I'm recording right now, and now I can share my screen. So alternate future Josh, once you're seeing this, you can go ahead and trim the video to right about now. All right. Okay, can you guys see my screen okay?
Yeah.
Hopefully. Excellent. So we're going to go over basically how to begin to plot our own surfaces mathematically in Rhino using Grasshopper, and a little bit of algebra and trig. So not to scare you at all, but we are going to relive some math that you probably did in junior high and high school. Okay, and I'm in Rhino. So first things first, I'm just going to do something that I haven't actually given you an example file for, but I just want to sort of set the table here. And let's review probably some stuff that you did a long time ago, if not sooner. But at some point in time, you probably had some sort of equation where you can pop in a value for one of the for a variable, right? And you get a variable, or you get an answer out, right? So you can evaluate an expression. Maybe you were plugging in an x value and getting a y value out. Then you take the x and the corresponding y output. You plot those on a Cartesian coordinate grid. You start plotting a bunch of points on the Cartesian grid, and then you draw a line or a curve through them, right? It's a way to visualize graphically a particular equation. And so that's what I'm going to do first in Grasshopper. And we're just going to talk about the widgets involved. And I found that this is the easiest way to then dive into doing the exact same thing, but three-dimensionally with surfaces. So instead of a piece of paper with an x and a y, we're going to be inside the Cartesian coordinate space with an x, y, and z. So if I think about this for just a moment, let me go ahead and turn my annotate tools on. I'll just draw. So at some point in time, you probably took the number line and you turned it and made an y-axis with it as well, right? And at some point in time, you probably talked about sine and cosine functions in trig. The idea being that as you plug in larger and larger x values into a sine function, the y values oscillate back and forth between 1 and -1, right? So if I give it this value in the x, it gives me this value in the y, right? And I have a set of plots I can point, or a set of points I can plot on the graph paper, and then draw my nice wave through them, right? All right, so let's do that in Grasshopper. This is the first step to sort of thinking about all the numbers and stuff under the hood when you're modeling and drawing. All right. So first and foremost, I need a set of numbers. I need a set of numbers as x values, right? Something I can plug into x and then find the sine of. So I'm going to go ahead and go to my sets, my sequence, and there's several different ways to create a list of numbers here. Series seems to be a good one. I'm just going to go ahead and pull that up just as a reminder, right? In order to make an ordered list of numbers in series, I give it the start number, the step size for each successive number, and then the number of steps or values in the series. All right, so this is going to start at 0 by default, step size of 1 each time, 10 times. Another big surprise, starting at 0, 1, 2, 3, 4, goes all the way to 9. Gives me a set of integers from 0 to 9. I'm going to go ahead, I'm going to plug in some number sliders into the input so I can begin to adjust that. First, step size. Also the number of steps. Number of steps, I'm actually going to double click here and constrain it to integers. I don't want 2.5 steps. I either want 2 steps, 3 steps, 9 steps, 90 steps, whatever it is. Set the maximum to something ridiculously large, like 1,000. All right. Now we can start generating some numbers here. Oh yeah, look at that. Okay, but I'm going to dial it back here to about 14 or so. All right. So we have a list of numbers: 0, 0.25, 0.5, basically starting at 0, stepping 0.25 each time, 14 times, pulls us up to 0 to 3.25. All right. Now, we have a list of
Josh?
values. Yeah.
I forgot, why does my slider only go up to 1?
Your number slider probably already just has a minimum maximum already set default to 0 to 1. If you double click on it, you can reset that minimum maximum.
Gotcha, thank you.
Mhm. All right. So we have a list of, let's say, X values. And now we need to find their sign value for the Y coordinate. All right. So I'm going to go back to the Maths tab. I can actually find a sign function here, I think. Let's see, where would that be? Right there, cosine, sine. But I'm just going to use the evaluate expression tool. What this will let me do is solve for a number of different variables if I need them, okay? So the way this works, right, is I give in the an expression, right? Let's say x squared. And then I plug in values for x, and then it outputs the result after it evaluates each of those x values through the expression, all right? So if my expression was, let's say, x plus 1, commit changes, I'll go ahead and set that to x plus 1, and I'll plug this in for x, right? And so I start with 0, 0.25, 0.5, 0.75. What this puts out is 1, 1.25, 1.5, 1.75. So just added 1 to each of those and spit out the results, right? Just as you would expect. All right. Let me go ahead and erase that. And I'm going to say for the sign editor, or expression editor, sorry, sign of x. Okay. So I'm going to find the sign of x, commit changes. Now it's going to give me a set of values for y, the kind of values that we talked about actually. So 0, 0.24, 0.47. You know, interestingly, you can see it gets close to 1, approaches 1, and then it starts to go back down, right? So 0.99, then it starts going back down to 0.98, 0.90, 0.77, etc. All right, so let's see what we actually have here. Let me go ahead and shrink this. But essentially what I said is that we have this list of numbers as our x coordinates, and then the resulting sign values as y coordinates. So really all we need to do is make a set of points and plug this list of numbers in for x and plug this list of numbers for y. Then we have our start of a sine curve, right? And of course I could change the number of steps and the sine curve can grow and grow and grow. I can also change the step size for each and watch it grow or shrink. Okay. Last but not least, I have these points. I can draw a curve through them, right? Just as you guys did back in Algebra 2 and Advanced Unified Math and other stuff. I'll just say interpolated curve, plug these in as the vertices. I'll go ahead and turn the preview off for these points, and there we have it. All right. So I'm hoping that this is at least striking a like, hey, wait, I remember doing this a long time ago, right? Please say yes. Okay, all right, good. Sorry. Now, what you'll notice here is that this expression editor, the thing I plugged in, the expression sign of x, right? Not only does it have an x input, it has a y input. And if I zoom in on it, it has pluses and minuses. And so I could actually take away or continue to add multiple variables. Boy, that would be some sort of expression to have 6 variables to plug in and solve for. Oof, right? But it's possible. And in fact, some of these we're actually going to do 2 and even 3 or 4, okay? And so I just wanted to bring that to your attention. What we're going to do is something very similar to graphing curves on a Cartesian coordinate grid. But what we're going to do is we're going to do it three-dimensionally. Okay. And so we're going to start again with this set of numbers. I'm just going to go ahead and disconnect this stuff so it doesn't blow up on me. Just start disconnecting things like this. We're still going to generate points. Be kind of fun. We don't need to draw any curves. Right? But what we're going to be doing is we're going to have to solve for both x and y and z, in most cases here. Okay. So we're going to have an expression to plug in values for x, to plug out x values, and then for y values, and also for z values. And then we'll plug those in. We'll have three of these. Right. Right. And so now we need to do is we need to plug in an expression for each of these widgets. And then we need to plug in our list of numbers. All right. So this gives us a list of numbers. There we go. And what you'll notice is that, thanks. What you'll notice is that in the actual Canvas page, I'm going to send you to this website. It's I think it's one of many. This one is called Parametric Surface Catalog or something like that. It's actually in German, so I don't know if you sprachen Sie Deutsch or not. It doesn't really matter. In most cases, you can actually let Google translate the page. I'll show you here in a minute. In fact, this is what it looks like. What you'll see is that there's actually about a list of 245 different types of surfaces. And as you start to click on each one, right, it gives you a visual description of the surface. And it also gives you the expression to generate x values, the expression to generate y values, and the expression to generate z values for a grid of points that can then be connected up into a surface. Okay. You can see this is very much an inside-out surface. It self-intersects several times as it folds in over itself. This is called Henneberg surface. There's another one called Mater's owl. I don't know why it's called Mater's owl. If I was really curious about that, I could look it up in Wikipedia or Wolfram's Math Lab. We'll actually be dealing with Richmond surface today. And so that's the example that I've already given you guys, but we'll do it from scratch a couple of times, okay, while we're here in person. So the Richmond surface, by Richmond surface, word Deutsch, blah, 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 blah. I don't even understand German. If you're really interested in the description, you can translate from German to English, but careful, be very careful when you do this. Watch these equations when I translate to English. Sometimes it can screw up the equations and get rid of superscripts, right? So suddenly it looks like I'm multiplying u by 5 instead of, having 5 as an exponent. So I'm just going to go ahead and go back to the view original. There we go. All right. Okay, so back to our example with sines and cosines. I have my list of x and y, or sorry, list of x values. And one of the key things you're going to do with the surface is that we have to start to cross-reference things. In other words, we're going to make a grid of sorry, I'm trying to think of several things at once here, of coordinates. All right, and then we're going to start plugging in that grid into the various expressions to evaluate here for x, y, and z. All right, so what I'm going to do is I'm going to use the cross-reference widget. I'm going to cross-reference this list of numbers also to this list of numbers. And what that means is that I'm going to start to get a repeat of these numbers over and over again. So instead of having 122 numbers spit out, now I'm going to have the square of 122. I'm going to have 14,884, because that really rolls off the tongue, as one does, right? Just go ahead and change that to 100, right? So it's a little easier to do the math in our heads, right? So we should have 10,000 values, right? The square of 100. All right. Now, if we plug these in for x and y, right, we should get a grid of points, 10,000 points. It'll be crazy. Not sure where they're located. Oh, sorry, I turned the preview off. There they are, right? And if we did that without the cross-reference, we just plugged in an X and a Y, right? We would just match up 0 and 0 and 0.25 and 0.25 and just draw a line of diagonal points. When we cross-reference them, we tell it to put it in a nice grid for us. Yeah, all right. Just as a friendly reminder. All right. So we're going to solve for X and Y and Z. All right. So let's think about this for just a moment. Let's say I want to actually translate the sine curve as a surface across the XYZ Cartesian space, right? One way to do that is we're going to plug in X and Y to each of these. Now, what it's missing still is the actual evaluation or the actual expression here, the actual equation that you're going to give it. Okay, but let's just take this out for a moment. That's sine of X. I'm going to go ahead and just say X. For this one, I'm just going to put in Y. Now we have a grid. Now watch. We have Z set as sine of X. But I actually want this to be a sort of sine curve swept across a sine curve. So I'm just going to change the function for Z to sine of X plus the cosine of Y. I think this will work. I can never remember if I have to add or multiply. Commit changes. Boom. Yeah. Oh, cool. Right. So a sine curve swept across a sine curve. Right. And of course, we have these as a set of points, right? Instead of drawing a curve through them, we're going to draw a surface through them, right? We have a nice grid of points. I'm going to go to the surface tab. And I'm going to go to freeform surface from a grid of points. Feed it the grid. Now it wants the number of points in the U direction. In other words, it wants the number of like points in a row. And that way it knows how to draw the surface. So it's going to get to 100 points, and then it's going to stop and go to the next row, right? And so what we're going to do is we're just going to give it, we've set that number all the way back here for the number of values in our series of numbers to start with, right? That's the number of points we have. It's 100 right now. That's going to change. So I'm just going to plug the slider into that. Right. Ta-da! Turn off the points. Let's take a look at the surface. There it is. Right. And of course, I could bake that in to Rhino if I wanted to, if I was so inclined. Right. So, but I'm not. Additionally, right, this is just the bare minimum we could do with, let's say, a sine function, right? So, for instance, if I wanted to change, let's say, the amplitude of the oscillation, right? Right now it goes back and forth between 1 and -1. Let's say I wanted to increase its height, right? I could add an extra variable right here, right? It's already named Z. I could put this in parentheses and then take whatever pops out and multiply it by 2. Commit changes, right? Now, instead of using 2, I'm just going to, you can see it got doubly tall, right? Instead of using 2, I'm just going to plug in Z. All right, now it's going to tell me I have an error because I haven't plugged in any values for Z. Here's where I can, again, plug in another number slider. I'll set the minimum maximum, plug this in. And now I can make this short or tall, jaggedy and spiky, ridiculously wavy, and on and on and on, right? I go back and forth till I vomit from something terrible like that. All right. Okay, So again, what we're doing is we're setting a function or expression to evaluate. Then we're plugging in values down below. And for each of these boxes corresponds to an X or a Y or a Z coordinate for a list of points that we then convert to a surface. All right. Now, I'm going to build this out one step further. And that is, right now, I have to hold my cursor over the function input in order to see the expression that I input by right-clicking and using the expression editor. One easier way I can do this that sort of helps me understand what I'm actually looking at is I can use a notepad. I forget what this is actually called. The panel widget looks like a notepad to me, like a sticky note. And I could actually type in the expression there, right? And then plug it in. So I'll use this one as y. Just pass out y. There we are. And then for this one, I'll say sine of x in parentheses, plus cosine of y in parentheses. I'm going to surround that with brackets or outer parentheses, and then multiply the sine cosine sum by z and hit OK. Right. And so instead of plugging it in here, or sorry, instead of writing it here, I can write it out here and plug it in. Sometimes it's a little easier if I want to edit it or see what it's actually doing. Right. Last but not least, if I'm really thinking ahead, I could also put another one of these here and say sine wave three-dimensional sine wave field or something like that. Sin? How about sine? There we go. All right. So what we're doing is we're generating a list of values in an incremental fashion. We're cross-referencing them in order to make a grid in space. And then we can pass those lists of numbers, cross-reference numbers, to three different expressions. Each expression pops out an X or Y or a Z coordinate. We pump out those coordinates into a point widget, gives us a lot of points. And then we can have those points, we can draw a surface through them using the surface from point widget. All right. And then over here, I even added an extra variable, right? So this is solving for three variables, X, Y, and Z. And there we go. All right. Does this conceptually make sense, even if you don't know exactly where I got all these widgets yet? You probably remember some of these, right? The cross-reference and making a list of points, plugging them into a point widget, you know. All right. Cool. But basically, that's all this is. The f sub x thing, you know, it looks really like, especially if you don't remember everything that you did way back in the day in high school, it looks kind of, well, it brings back bad memories and scars to me, but it's not that bad. Now that you actually have a reason to do it, instead of, back when I did this in math class, I was like, what am I doing this for? I don't even really understand what I'm doing. It's actually pretty good at it. Didn't really have any idea what the practical means for using it was. Enter, if you like architecture that relies on geometry and math a lot. So, okay. So again, that's not an example that I've given you, right? But this sets the table now. So when I open up the example that I gave you, maybe it starts to make sense and we can read it. Okay. I'll start over here. This is called a Richmond surface. And we have an expression in this panel to solve for X coordinates, an expression in this panel to solve for Y coordinates, a panel here to solve for Z coordinates. Last but not least, in order to generate our list of numbers, we're actually giving it a minimum maximum and then dividing up between the minimum maximum in number of times in order to generate numbers. What you'll find is that a lot of these surfaces don't necessarily continue on and on. If they're periodic, in other words, they close in one direction or the other, then you'll notice that they actually have a minimum maximum value. Sometimes it's -1 to 1, in this, like in this case. Sometimes it's -4 to 4. Sometimes it's -3 pi to +3 pi, whatever it is, right? Oftentimes, they'll talk about that right here. So instead of using X and Y, this website annoyingly uses U and V. And so it's giving you the range, the minimum, maximum, the domain for the solution space here. So -1 to 1, -1 to 1 for both U and V, okay? And so what I do is I take that domain, -1 to 1 for X and Y, I plug it into the range, which gives you a minimum maximum, right? Wants a minimum maximum, and then wants the number of times to divide in between that minimum maximum in order to generate a list of numbers that fall, between -1 and 1, right? So starting at -1 all the way to +1, 36 divisions inside, you start to get a list of numbers, and a new number line, so to say, right? So I do that for both of these, X and Y, just in case they might be different. I want to change them later. The number of divisions, of course, is a variable. I cross-reference them together, just like we did before. I have a list of numbers. I cross-reference them. And then I'm basically cross-referencing the A and the B. Those are X and Y, right, for each of these functions. So I'll do the same thing. Oh, sorry. It's the same thing over here. Looks a little difficult maybe to follow some of the lines, but you can see all the A's go to X for each of these. This is X, this is Y, this is Z coordinates. And the B's go to plug in for the Y. Right. Now you can see here, where did I get this? -3 times X minus X to the 5th plus 2 times X to the 3rd, and on and on and on. It's kind of a pain. I got it right here. Right. In fact, I was able to copy and paste this and then add a little bit of, a caret for the exponent. Grasshopper actually wants you to add the asterisk for multiplication. It doesn't let you put a constant with a variable unless you put that plus, minus, slash for division, or asterisk for multiplication, right? It pops out X, Y, and Z coordinates, which are popped in for points. Just turn the preview off here. It gives you a list of points like this. And when we make a surface from it, the surface looks like this. Turn the points off. It's a massive surface for just a little pucker at the end. Now, one thing you'll notice here, hopefully you notice this, you can notice it on my shared screen. My background is set to white. You can see the grid, and my background color is set to white. In here, where there's supposed to be a hole, you can see that there's actually pink there. In other words, the constraints of Nurbs surfaces, it doesn't like a surface with a hole or a tear in it. And so what it's done is it's actually wrapped surface back in on itself. Okay, and I'll talk about that in a little bit. Okay, but essentially, ta-da, we've actually solved a Richmond surface in Grasshopper. There's the surface. I can go ahead and bake that in to Rhino. Let's do that right now. There we go. I can turn Grasshopper off. There it is. Look at those isoparms. They look like rings or loops. Some of them even look like concentric circles, but they're not quite circles. There's anyway, sort of a really interesting conformal deformation here. It's pretty weird. Now, again, we're having a problem where you can see the gray. Simply, the surface becomes periodic by itself and closes in on itself. Okay. Now there is a fix for this. If you have Rhino 7, right? One of the things I can do is convert this to sub D, and then I could start to delete certain faces away, right? I'll go ahead and do this for you really quickly. Don't worry about following along. I just want you to see what I'm doing, right? And just know when you come run across a problem like that, there's a way for us to solve it together, one way, shape, or form. If you don't have Rhino 7, then you can give me the file and I'll solve it for you in Rhino 7. But what I'm going to do is I'm just going to say selection filter, and I'm going to pull this up. So once I make a sub D object, I can start to select different portions of the sub D object. I'm just going to go ahead and say convert this to sub D. Use any creases and corners? Yes, I just want this to try to use the exact same shape, approximate the sub D geometry in between. And I'll go ahead and hit enter. All right. There's the surface. I'll go ahead and move the surface out of the way. So that's the sub D. Yeah, it sure is. Look at that. All right. So I'm going to I'm just using these tabs along the top, going back to the sub D tools. And I have a selection filter where I can say, I just want to select just the faces or any face of a sub D. I can select that weird scrambled face and delete it, and it's gone. Then maybe I want to get rid of how large the saucer around the surface is. I can start to just erase. Focus in on the good stuff, which is the sort of inflectional tear at the center. I mean, the interesting part of the surface isn't all this stuff. It's right here, right? I mean, that's pretty crazy. Oh, sorry. Let me just recenter my, oh. All right, let me try to be a little smarter and recenter my rotation, right? That's tight nasty, am I correct? I mean, holy moly. And that's really harder than hell to like model manually, right? So when it suits us, we can actually use geometry to our advantage. And that's what part of what we're going to start doing to discover interesting geometries and surface patches that we can use for our inside out assemblies. Sorry, it's been a weird day. And my wife just brought me in like some McDonald's because it's Friday and I don't do shit. So hope you can get over my eating some French fries that are starting to get really cold, which is nothing worse than cold French fries. So there was the surface. That's the sub D version. The other nice thing about this is I can always convert this to a mesh or a polyspec to a polysurface. Sub D, convert object to Nurbs. I'm going to go ahead and turn that selection filter off and just select the entire sub D object here. Where is it? Convert object to Nurbs. There we are. Delete input objects. No. I'll go ahead and just hit enter. There's the open poly surface. I'll go ahead and move that off here. The Rhino files I gave you, if you open it up in Rhino 7, you'll notice that there's this, and then this, and then this, right? So don't worry, even if you don't have Rhino 7, if you need this done, we can do that somehow by sharing our systems maybe, and then always convert them back to poly surfaces. And then these poly surfaces can be cleaned up. A little goofy here at the end with the isoparametric curves, interestingly enough. Or if you were so inclined, you could actually convert this into a mesh and actually requad the mesh to make a nice clean mesh with only quad patches. I think that's right over here, quad remesh. Oh yeah, let's try that, why not? Sometimes it takes a while. Target quad count. Maybe I'll lose about half of those to set it to 1,000. Let's see how long it takes. Crane quad mesh up to 32%. Give me some French fries. Hey, at least they're salted. Nothing worse when you get in and out French fries and they're soggy and they're not salted very well. Oh wait, this is McDonald's. Yeah, McDonald's is all right. Friday, I need me some in and out. Just sort of curious what this does. Now, don't worry, I'm going to go ahead and we'll start this over from scratch. Okay. In Grasshopper, so you can see. Let's see what that mesh did. That mesh is now a really, man, how uniformly spread out is that? Wow, it's not so bad. That's pretty good. I thought Rhino 7 was kind of rushed in its release, but these are significant tools that they added here. I'm actually pretty happy so far with my investment and what it's worth. Again, if you want to play around with these sort of things, I mean, there are a number of different ways you can play around. If you're in Rhino 7, again, using the sub-Ds, you can begin to do things like reflect, give an axis by which to, around which to reflect. Let's see. And start to play all kinds of crazy surface games. So the surface flows into another surface. And, there might be some cleanup here to make this actually look kind of smooth. It looks smooth there in profile, but here sort of bows outwards. So, at that point, you can look at some of the sub-D tutorials that are actually pretty quick, and you can begin to clean this up. Maybe I select an edge loop like that one, and cannot delete. Why can't I delete an edge loop? Yeah. Oh. I keep selecting the wrong darn thing. It's really frustrating. I'm sure you guys can sympathize with that. Try to delete. Right? And so on and so forth, right? I mean, you can begin to, you select the right thing here, you can begin to, sorry, I need an edge loop. There we go. You can move edges and things like that, slide them. Where is it? Not that I'm very good at this yet. What I like is I don't have to use T-splines because, man, that was the worst sometimes. Slide. I guess you can just move it, but there is a way to slide edges. There's also a bunch of shortcut keys, so I recommend that you use that that tutorial. Right. Okay. And so as you go through this catalog, you can start to see a number of different surfaces just using math. Right. It's not that this is a really interesting surface, but we could start to use portions of these surfaces. What's interesting is that you can begin to reflect and use different portions of these surfaces as patches and then begin to deploy them in order to create all kinds of different interesting things. Okay. And, I'm thinking of envelopes, building skins, courtyards, entrances, the transition between indoors and outdoors. I think one of the key things here is how we can begin to make a aggregation of these shapes subdivided and then begin to cut them in sections and start to see the potential for new ways of ordering and giving form to architecture. So that's one of my ulterior motives here, is to start to explore these geometries that don't typically work for architecture, but suddenly, let's say we need an architecture that can breathe, and it doesn't really, there might not be so much of a distinction between indoors and outdoors in some places and things like that. And inside out sort of architecture, maybe we start with inside out geometry, right? That's the one of the premises of the studio. right, that we have a chance to explore, right? So we'll actually go through these here in a little bit and make a short list that I'll actually publish on the page for you guys to experiment with over the weekend while you're also doing your readings and watching that film if you haven't yet, okay? As an initial sort of experimentation. Over the weekend, the experimentation is just that. It's have fun, try your best. You're gonna mess up a couple of times. Bring the mess ups, bring the things that worked and the things that didn't work, and we'll work through them. That's how we learn, okay? All right, so enough about that. Let's go back to Grasshopper. Let's try this again. Oh wait, that was just the edges here. Here we are. Seriously? Oh, the selection filter's on, so I'm just selecting sub-objects. Boy, that's really annoying. All right, I have to get used to that. Cool. All right, so there we go. Here's an example down here. This is an example I gave you. This is a hyperbolic paraboloid. This has 4 variables instead of 2. So it has the standard 2 for x and y, a list of numbers with a minimum maximum, cross-referenced and plugged in for x and y. But then we have some multipliers for height and spread plugged in for z and u, right? Let me go ahead and turn this one off and I'll show you this one, just so we can sort of take a look at that. Disable that one. And I'm going to select all of this, say solution, enable selected. You'll see that this is basically a hyperbolic paraboloid. In fact, it's labeled as such. That's a fancy word for saying a parabola. You can see a parabola here, right? Swept across a parabola in the other direction, going the opposite way, right? Yeah, it's just a parabola swept across a parabola. And really, x and y are so stupid. It's just x and y, you make a grid. And it's z, where we say we take y squared over u squared. Then x, and then we subtract from that x squared over z squared. We also have a minimum maximum that we can change here. -10 to 10 is the space that I've typed in here, but we can always retype in a different set of constraints. Let's go with -5 and 5 for the x. And you'll see one side gets smaller, right? While y is still the same size. We can always change y as well if we wanted to have some parity here. -5 to 5. Right, and it's going to get smaller. Okay. In other words, we're just changing the amounts of the spread along the x and y axes of the values that we're generating. Anyway, all right. Same thing though, right? -5 to 5. We divide it 40 times, 41 values. We plug those in, cross-reference them, plug them in for x and y. And then we also have a set of sliders that can adjust the curvature. Now, what's interesting about this, you notice that the larger the value, the shallower the curvature gets. In other words, the smaller it gets. And that's because this is plugged in for z and this one's plugged in for u. Those are used in division, right? So the smaller the number, the larger the value. The bigger the number that you divide by, the smaller the value out, right? So as we approach 0, this thing gets really distorted. Right? And as we get larger, it gets less and less saddle-like, interestingly. Okay, shallower. Yeah, but it's just right here. There it is. There's the points. There's the surface. Turn off the preview. There it is, right? That's the textbook hyperbolic paraboloid. All right. And really, it's no surprise, right, that we'd be squaring one input and subtracting something from. That's how we make parabolas anyway, right? Exactly, right? Yeah. X squared minus 1, etc. Right? So y equals x squared. That's a parabola. Coolest, simplest exponential growth algorithm ever. Anyway, that's that. Let's go ahead and start from scratch. All right. Now, the reason I gave you this example to use is because essentially it's a template, right? For instance, well, let's build it first, and I'll talk about it as a template. Because what we'll do is we'll build the Richmond surface from scratch, right? We'll go through that process one more time together. And then what I'll do is I'll save that, and then I'll change it from a Richmond surface to maybe an Inniper surface or a Catalan surface or something like that, okay? What we're basically doing is changing the expressions and then changing the domain, the minimum maximum for X and Y. So that's all. So we'll start to change things and we'll get dramatically different results as we go. Just add the chat box over here so I don't lose it. It just disappears on me when I share my screen. All right, so am I missing anything? No, I'm not missing really anything. First things first, we know we're going to make, well, let's work backwards. I know we're going to make a surface from points. I know I'm going to have a point widget that I plug X, Y, and Z into, right? And that this will give me a grid of points that I'm going to plug in here. Everything's going to be yellow because there's really nothing here, right? This is just 0, 0, 0. That's 1 point. You can't really make a surface from 1 point. You need at least 3 points to define a plane in space. So let's see here. Right. And so I know I'm going to need these expressions. And I'm going to go to math. I'm just going to find that f sub x evaluate icon. There we go. I'm just going to copy and paste it. I know I'm going to need 3 of them. 1 for x, 1 for y, and 1 for z. Right, now, I need the functions or the expressions that plug in here, right? I'm going to go ahead and make me a little notepad. Copy and paste that one. That one's going to be this one. Dun, dun, dun. And that one. You know, I can even right click and name this. I'll say f sub x, right? We're going to find x there, x coordinates. Here I'll say 5f sub y. You don't really have to do this, but it just helps me sort of understand later on, a month from now, when I open this up and I go, what the heck is this? As I'm wanting to do sometimes. All right. Now, I need to know what these expressions are. So I'm going to go ahead. In this case, I've already have my Richmond surface up. I'm just going to go ahead and copy and paste this in. Let's see, doing this from the Mac to Windows. So Command C, in my case, double click, and then Control V here. Just expand this out a bit. Now here's some problems, right? We have some spaces where we don't need them. And I need to put some multiplication there. This is actually, this 5 is an exponent, right? So I need to put a caret there. So -3 times u, and then u to the 5th. We're going to have them calculate those, right? Then subtract them. 2 times u to the 3rd. So we'll go ahead and add, oops, sorry, a caret there. And an asterisk there. Let's see. Yeah, 2 times u to the 3rd times v to this v squared. So I need also a caret here for that exponent. It's kind of annoying to have to write it this way, isn't it? C'est la vie. All right, 3 times u times v to the 4th. Is that what that is? 3 times u times v to the 4th. Yes, okay. So we just need to add some, well, first we need to add a caret here for this exponent, right? V to the 4th, you put a caret in front of the number meant to be the exponent. Now I'm just going to add an asterisk there, an asterisk there. Oop, in the wrong place. There we go. Right, and so as you start to remember the order that it does arithmetic, right, it'll take care of of exponents. They'll take care of multiplication inside those parentheses. They'll take care of addition and subtraction inside those parentheses. And then last but not least, it'll do the division between, everything at the top and everything at the bottom here. So we have now, what is this? 6 times the the sum of u squared plus v squared. All right, so let's do the superscripts first. Caret for exponents, caret for exponents. 6 times everything inside these parentheses, right? So it's going to square u, it's going to square v, it's going to add those together, then it's going to multiply by 6, then it's going to use that and divide the numerator with, right? So, okay, there we go. Hopefully that works. Every once in a while I make some typos here. Sometimes it likes spaces and sometimes it doesn't. I don't get how that works. Maybe it's just me. Probably just is me. Oh, okay. Sorry. Now we do the same thing for y. I'm gonna go ahead and copy and paste this. Yeah, this might take 5 minutes, but then I can generate all kinds of stuff with it. Let's hit the wrong key there. All right, there we go. U to the 5th plus 2 times u to the 3rd times v to the v squared, v to the 2nd. So here we go. Caret, caret, asterisk, asterisk. 3 times u times v to the 4th. Caret. And we'll make sure that it knows to do multiplication there. Some asterisks. Okay, we have division 6 times the sum inside these parentheses, which is u squared plus v squared. Add those carets there. Make it nice and explicit. There we are. Perfect. And then last but not least, z, we just use u or x, right? Now, what's interesting is that this is using u and v. The Rhino by default names these x and y. So watch this. I have to change all of these u's to x's. I try to do this in a way that I won't like get messed up. So I just first of all, I make sure that it like is kosher with the actual math, the actual operations. And then I go back through and rename the variables here as a second step. And that way I don't get confused and forget one thing versus the other. So I'm going to go ahead and convert u's to x's. If you're using Microsoft Word or Notepad or something like this to do this outside of Rhino to start with, you could easily do a find and replace. Change v to y, u to x, v to y, u to x, v to y. All right. For f sub z, right, we're just going to use u or x. So I'll just put x here. Right, so we'll just take the x values and spit them right back out. Awesome. But we need to actually put in a bunch of x and y values here. All right. So it's telling us that for u and v, or otherwise x and y, right, we need a range of numbers between -1 and 1. And then also for v or y, list a range of numbers between -1 and 1. All right. So rather than using series to create a list of numbers, I'm going to use range, because what that lets us do is set that minimum maximum. And so all of our numbers are going to be between that minimum maximum, between or equal to, right? So for the domain, sorry, just so this doesn't look so sloppy, I'm just going to go ahead and arrange these all the same width. I don't know why I'm so anal about that sometimes. All right. I'll go ahead. I'm just going to go ahead and type these in here. So in this case, I'm going to say -1 space 2 space 1. That's how Grasshopper likes domains set up. -1, 2, 1. There we go. There's that one. We'll go ahead and give it a slider here, constrain it to integers. This is the number of divisions, so I'm going to go ahead and set a minimum of 1 and a maximum of something silly like 100, something really large. Why not? Plug this in for both of them. I'll make a square grid. There's my x. Here's my y. Oh, what did I forget to do? I forgot to cross-reference them, didn't I? Bad, Professor Vermillion. I need more French fries. All right. And so I'll actually take a second and actually select. I usually don't even bother to do this. Actually pull these out a little further. Try to straighten this out a bit. There we go. You can actually justify those, center them all together. I just never bother. I don't know. Anyway. All right. So we need a cross-reference. Go to sets. There's the list cross-reference widget. Cross-reference these against these. Now I can plug them in for x and y. X and y. X and y. All right. Now we have a couple of errors here. I'm wondering if I messed up an x and a y somewhere in here, or maybe I still have a z. Let's see what it gives me. Expression generated error for x, y, division by z. Division by 0. Oh, that's interesting. I wonder if this makes a difference. It does. The number I'm popping in here makes a difference, whether or not I have 0 or not. Oh, that's kind of cool. Huh. So this looks artificially stretched. What I've done is I've made some sort of goofy mistake here in the x and the y. So let me just double check that. -3 times x minus x to the 5th plus 2 times x to the 3rd times y to the 2nd plus 3 times x times y to the 4th. That's all being divided by 6 times the sum of x squared plus y squared. Well, that looks fine. -3. Here we go. That should be a y. That looks so much better. That looks like a healthy Richmond surface to me. All right. Now, again, you can always play around with this. What happens when I change this from -1 to 1? And I change it to -10 to 10 or something like that. I make it much larger, right? Sometimes you break these things, which apparently I've done somehow. See what happens when I change this one as well. Maybe it just gets really large, who knows? Maybe the universe implodes, beats me. Ugh, that's not good. Note to self, don't change the domain that extremely. Okay. So we're still getting an output here, division by 0. I'll go ahead and change this number. And then input parameter, we still need to plug this in for you. I'll go ahead and plug this in. Now look, we're dividing 39 times between a minimum and maximum. So we're actually gonna get this plus 1 is the number of values out. So let me go ahead and write that expression here for you. I'm gonna say whatever is plugged in for this, add 1 to it. And then I just plug this in. So if it changes, there, no more red, no more yellow, no more orange. Yeah, interesting. Cool. Wow, wow. Okay. As I said before, right, this can serve as a template for you. So once you have this, and I've given this to you, as well as we've been putting this together in person, step by step here, or in class, step by step here. We could always change this. Let's say we want to change it to a snail surface. A couple of things I'm going to do. First, I'm just going to not generate a list of points here with these until I've made all the changes. I'm just going to go to the U and the V right? That's the minimum maximum. It's to say, let's see, instead of -1 to 1, it's going to be 0 to 2 pi. Of course, right? I'm just going to go ahead and change this. 0 to 2 asterisk pi. Should recognize pi when I write it like that. Better. I don't actually have the Greek character here. Okay, then negative pi to positive pi. Okay, interesting. Let's try it. The worst that could happen is Rhino crashes, my computer explodes. On second thought, that actually sounds really bad. Okay, so X, Y, and Z, except annoyingly, we're using X's instead of U's and Y's instead of V's. Okay, so we got X times the cosine of Y times the sine of X. Basically, I'm just going to copy and paste. It's pretty straightforward. What in the world? Chunks. There's a little bit of HTML in there, I think. Hey, what did I do? Oh no! Just kidding. I just delete it. Probably quicker just to delete the whole note and start over. Okay, that's weird. All right, so annoyingly, I'm just going to pull this over here so I can see at the same time on my screen as Rhino. And I'll just manually enter it in. So X times cosine of Y in parentheses, and then also times sine, and in parentheses, X. Dun, dun, dun. All right, now, if this one will be X times the cosine of X times the cosine of Y. Yeah, X, U, V, so X, X, Y, cosine, cosine. That one was cosine sine. All right, yeah, whatever. And then -1 times X instead of U times the sine of Y instead of V. All right, let's see what we have here. Hey, that looks like a snail surface. Oh, weird. Why don't I zoom in on it so we can actually see it? Yeah. That's uncanny, isn't it? Look at that. Wah, wah, wah. All right, cool. What's weird about this one? I kind of want to bake this one in. See what that looks like in Rhino. Maybe. Break. All right. Okay, yeah, sure. What is that doing? Oh, yeah, look at that. That's crazy. What? That's sick. That's pretty cool section, cross section through there if you cut it. I don't know what to do. Let's sub D this bad boy. Yes, yes, yes. There we go. Twisty. Interesting double skin here, right? And what's inside versus what's outside? That's what the hardest thing I have in having trouble sort of visualizing here is how do I maneuver around this thing? Do I hit a dead end? That'd be bad for life safety. Just saying. You guys are like, I can't believe Vermilion thinks this is architecture. Could be. Oh yeah. So there's the inflection point. There's where two pieces of skin crash through each other. That'd be a pretty cool architectural statement to exploit and celebrate, actually. Two different material systems slamming into each other like that. Interesting. That's where it happens. It has to self-intersect, and that's where it happens. Cool.
Hey, Josh.
Yeah.
Quick question, but when I do convert to sub D, it turns the shape into very polygonal. If that makes sense. Like it's no longer curved; it's flat surfaces.
Um, Sit tight with that. And what I'll do is after the session's over, I'll stop recording. We can do some troubleshooting and I'll have you share your screen and show me. Okay.
All right.
We're almost done here. So, right. So once you have this template, it's actually not so bad sometimes to, again, we could make this in a per surface. We could make this this is pretty interesting. This sine surface. Wow. Wow. That's a stupidly simple set of expressions. Huh. Yeah, why not? Here. Right. Let me just move this over here. Right. Sine of x, sine of y. Sine of x plus y. Negative pi to pi, negative pi to pi. So essentially just this, copy, paste. Drum roll, please. Oh wait, this is the thing I actually made in Rhino. Let's see how many of those did I actually make. Oh, pretty cool. Look at that. I'm easily amused, but even for me, I think that's pretty interesting. Bake. That one wraps in on itself a bazillion times. Interesting. Maybe less interesting than I thought. All right. So I'm gonna go ahead and stop sharing. I'm gonna go ahead and stop recording.